to make an enzyme complex, and then this enzyme complex can react to recreate the enzyme and form a product. And we're going to assume this step is irreversible, or the other way of looking at it is we're assuming that we're at low concentrations of our product in order to derive our rate expression. And then what we're going to do is look at the case. So non-competitive inhibition has also been referred to as mixed inhibition. The idea here is that we have an inhibitor present that could also react with the enzyme to make a complex. And this complex now is inactive, meaning it can't react further to product. It can, of course, dissociate back the enzyme plus the inhibitor. So an additional step is that the inhibitor could react with the complex. So instead of just reacting with the enzyme, it's also possible to form another complex which has both the enzyme and the complex. And then the final step is that we can form the enzyme substrate inhibitor complex by having the enzyme inhibitor react with the substrate to form the same complex. And so we're going to use the idea of rate determining step, and we're going to say this formation of product. So the rate that product forms is the rate constant for that second step times the concentration of this enzyme substrate complex. The other steps are all in equilibrium. Now we're going to write the equilibrium expression for the reverse step because of the form that this takes. That's the commonly used form. And so we're going to write a dissociation constant, which is the enzyme substrate complex dissociating. At equilibrium, we'd have the concentration enzyme, concentration of substrate, divided by the concentration of the complex. Now what we're going to assume is that for the substrate in this step here, reacting with the enzyme inhibitor complex, it has the same dissociation constant as the substrate reacting with just the enzyme. In other words, the binding of the inhibitor doesn't affect the equilibrium for the binding of the substrate. So what that means is then we're going to have the same dissociation constant, and I'll write down the expression. And then we're going to have another dissociation constant for the inhibitor reacting with the enzyme. And again, it's the same form, concentration enzyme, concentration inhibitor. And then finally, we're going to assume the same dissociation constant for this step. Again, the idea that the inhibitor reacting with the enzyme or with the enzyme substrate complex has the same dissociation constant. The fact that the substrate is bound to the enzyme does not affect the equilibrium for the inhibitor to bind. So I'll write this down. So the final piece we need to obtain the rate expression is that the total enzyme concentration does not change. In other words, enzyme's a catalyst, if you like. And so it's either the free enzyme or it forms a complex with the substrate, or it forms a complex with the inhibitor, or it forms a complex with both of them. Add all this up, we should have the same concentration of total enzyme as a function of time. So what we're going to do now is substitute into this equation using these equilibrium expressions that we just wrote down. So let me pause and do that substitution. Now our goal is to obtain expression for the concentration enzyme complex. We can substitute here so we can get a rate expression in terms of the measurable variables. namely the substrate concentration and the inhibitor concentration. And so this equation for the balance here, we could solve for the free enzyme concentration. I could substitute back into this equation and get the enzyme substrate concentration. I could then substitute here. However, first I have to substitute here. I'm going to use this equation. So then I can take and solve this equation for the free enzyme concentration. Okay, so I've made this substitution. These other three terms are the same, so this means I can now write the total enzyme concentration. I can factor out just the enzyme alone, its concentration. Let me do that. So here I factored out, and so I can now rearrange this to solve for this enzyme concentration. So now I'm almost finished. I'm going to go back over here and let's divide so don't overlap the equations. The rate that I'm making product, the rate constant for that rate determining step, and the concentration of the enzyme substrate complex I can get from here. Enzyme concentration, substrate concentration divided by Km. And now I can substitute this here and I'll get a final rate expression. And so let's create a little more room. Let's do that down here. So the rate constant, E sub t, substrate concentration, Km, and now this term in parentheses. Okay, so we're essentially finished, but let's put it in a form that's a little more commonly used. And so what we're going to do is take this term, we're going to call that Vmax. This is the standard notation that you will see. So the rate that we're making product is going to be Vmax, the substrate concentration. Now, for the denominator, I can rearrange this. I can put together terms if I first multiply through by Km. Let me do that. And then I'm going to put together in denominator, so the rate, let's move up here, the rate product formation. So what I want, the two terms that contain Km. 1 plus initiator concentration over